The second part is related to going into specific distribution models or system that actually appears out there in the world. I already mentioned a few, and we have some specific sort of small f's and capital F's that are good choices for us in different specific contexts. And one of the very well-knowns, we could say, is the one we begin with, the binomial distribution, the coin toss model, you could say. The coin toss model, I tried to say. So we're going to start with this one, the binomial distribution as the first out of 3 distributions today, 3 discrete distributions. Now the binomial, we could call it the coin toss model. The probability model for the coin, sort of the random coin toss system, if you want to use this terminology. So, I'm going to do a little thing. I'm going to say that we have 3 independent trials. So we throw 3 times with a coin. It can be either success or failure. That would be heads or tails. The probability of, let's call that success. That's a generic term. Let's call that heads here. We call that P. I'm going to go down in the bottom and use a bit of writing here. Binomial distribution. We throw 3 times with a coin. Actually, it's not, you can do that on the internet, but anyway, I thought that's a bit naive to stand and throw coins on the internet. But if you try to Google coin toss on the internet, and you can play around and cost coins, 3 coins, or whatever. But I think we can all imagine the game here, that we throw 3 times with a coin. I do say that the probability of heads, which I've called the success here, I call that P. Of course, in many cases, you would expect it to be 0.5, 50-50. But I'm just leaving a little slot open here for the fact that maybe it's not exactly 50-50. Maybe the coin is not symmetrically. Maybe it's a teasing coin where you can actually make it asymmetric to have not a 50-50 chance of, but maybe something else. So we'll be as abstract as that. Maybe there is some other. Then let's start think about what can happen if we throw 3 times with a coin before going anywhere else. We can have heads, 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 tails, heads, tails, heads, heads, tails, tail. And then 4 more, right? Where I take the same, but start with, if I can restrict myself to 1 line, tails, head, head, tails, head, tails, 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 head. I should remember not to mumble too much, I realized. Tails, tail, difficult. Tails, tails, head, and then at the end, tails, 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 right? These are the 8 different possibilities. If I focus on the exact what happens from throw to throw, right, 1 throw at a time. At least now, if P was, if it was symmetric, right, then of course I would say using some of the basic rules, axioms of probability, where you multiply things if they're independent, then there would be 1/8 chance for each of these individual outcomes. If you focus on one individual of them, they will appear in 1 out of 8 cases. I hope you can follow me there. I'm not going to dig more into that. However, we are going to be slightly more general now, as I warned about. We're going to think about a general P. A general P means that the probability of tails is 1 minus P, right? P1 minus P, adding up to 1. It's a meaningful probability system for the basic event. Anyway, what is the probability for 3 heads now? What is the probability for 3 heads? 1 head was P, 3 heads. Don't you want to play with me? It's okay. Sorry, I didn't see you. Once again.
1 divided by 8 is times a half.
Yeah, but that was using this, and when you say that, that is assuming that the P is 0.5. Now, I don't want to assume 0.5 for now. I want to be slightly more general. I would say then, I mean, the 1/8, that's 1/2 times 1/2 times 1/2, right? That's a 1/8. Then I would say, obviously, it would be P times P times P. Wouldn't we agree? For it to be heads each time, it would be P the first time, P the second time, P the third time. So 3 times in a row, that would be P to the third. How about heads, heads, tails? Well, it's a P times a P times the 1 minus P at the third outcome, right? P times 1 minus P. We are assuming that the individual throws are completely independent of each other, that they don't interfere with each other. So I would say this is P squared times 1 minus P. What about heads, tails, heads? P times 1 minus P times P. Now, and when you multiply things together, again, as you know, the order of the terms doesn't matter. So, again, because there are 2 H's and 1 T, it's P to the second times 1 minus P. Now we can continue. We have 1 heads and 2 tails. We have 1 head, sorry. We had again 2 heads, 1 tails. We had 1 head, 2 tails, 1 head, 2 tails, and at the end, 3 tails outcomes. These are the 8 possible individual outcomes, obviously adding up to 1, like this one. Now, I didn't actually tell you what I was primarily interested in, and for it to sort of exemplify directly what we call the binomial distribution, actually the random variable that we're interested in, the random variable which we say has a binomial distribution, follows the binomial distribution. This is the one which counts number of heads. I use this double thing here to say counting the number of heads out of the 3 choices, right? I am primarily interested now. That is a decision I made. What is important to me at the end of this is just how many heads did I get. We could also have chosen tails. It's 3 minus the other. But we choose one of them and say, I'm interested in the number of heads. I don't care about the order now. I mean, in other contexts, you could care about the order, but for now, I don't care about the order. I'm just interested in the number of heads. What are the possible outcomes for this random variable? This is a random variable. It has, I would say, the following 4 possible outcomes. There could be no heads, there could be 1, there could be 2, there could be 3. 3. Making 4 possible outcomes, right? To control this system, to know all the probabilities, we need to find out what is f of 0, what is f of 1, what is f of 2, what is f of 3. When we know these 4 numbers, we're on top of the system. I mean, this is probability theory. This is getting on top of a random model for some system, and when I know the probabilities, I can deal with it for the future. I know not exactly what's going to happen, but I know the probabilities for what is going to happen. And this is what I can use to be intelligent for the future, knowing the probabilities. Anyway, what is F0? What is the probability to get 0 heads? I would say to get 0 heads, that only happens in, maybe I should say, this is like x equals 0. And when all 3 are tails, I get 0 heads. So in a way, it's a repetition. This must be the probability for getting 0 heads, right? So it's also easy to find the probability for all of them becoming heads, to take the 2 easy ones. That would then be the top one, p to the power of 3, which is the one we see here. Then the 2 intermediate ones. We need a bit of counting. And that's the point here. We need a bit of counting to find out what is f of 2, say, which is the probability of getting 2 heads. Then we should try to identify which ones are actually, maybe I should have a heading here saying capital X. And then I could say, which ones have 2 heads here? This one, and this one. 3 of them are having 2 heads, right? There are actually 3 of them that conveys to the probability of achieving exactly 2 heads. The good story is, of course, that these 3 in their sort of this theoretical expression are exactly the same by definition of the probability that I just wrote up. So actually we could take this expression from each individual of them and multiply by the number of count, the number of times that they are there. Because then we get the one probability plus the other probability plus the third probability. Say either it's like this, like that, or like that. There are 3 different ways that 2 heads can occur. So we add the 3 probabilities together, and the 3 probabilities are the same. So we say 3 times the same probability. Exactly the same story goes for f equal 1. That's the remaining 3. There's a 3, but then it's p times 1 minus p squared. Now I know the 4 probabilities, at least if I know p. I mean, given p, I'm on top of it. What I've done here is actually more or less to derive or prove, even at least in a small situation, what is known as the binomial probability formula. The general formula, as you can find it in the book, is here, which is the formula that I've been playing around with. Number of heads, p to the number of heads, 1 minus p to the number of tails, and then some number in front of it, counting how many times the event will be on the list. For our case, it was 3. This number is the binomial. Say this one is the binomial coefficient. This is the one that I've given you some pages in chapter 3, because there it's defined explicitly to us. It's a binomial coefficient, n over x. It's a combinatorial measure, telling us how many times can I take x and x subset out of a group of n. How many times could I take one outcome out of a group of 3? Well, it could be the first, it could be the second, it could be the third. It's much more difficult to find out how many different ways can I take 7 out of a collection of 100. Well, it could be the first 7, then it could be the first 6 plus number 8, the first 6 plus number 9. There are many, right? And then after the first 6, then you start. It's a long list of possible ways of seeing 7 out of 100. Now there is a formula for this combinatorial number, for this count number. And that's the binomial coefficient. It's given by the n factorial divided by x factorial, and also divided by n minus x factorial. Factorial is the 5 factorial is 5 times 4 times 3 times 2 times 1. That's the name for this thing. So there is a rule for doing this counting. Phew, we don't have to think each time. We can just apply the rule for counting. right? This, we can use the binomial distribution by tables or by R, and we're going to exemplify this. The accumulated probabilities are given in the tables, and both small f and capital F are given in R, actually. So we skip this one for now, and let us say now that we have done the general description of the binomial distribution, George, so we go on to the next little thing.